Yes, welcome to machine learning. Today we will talk about machine learning, what it is, what it is made of, and the different types and concepts that are entailed within machine learning. Yes, what is machine learning? This is basically a field of study that gives computers the ability to learn without being explicitly programmed. In the simple man's language, you would say it makes the computers intelligent, that they can pick patterns and adapt and behave differently based on the patterns they pick from a given set of data. And someone would ask, why do we need machine learning? It is useful in complex tasks that require a lot of rules to be written to accomplish the task. The learning algorithm will write these rules based on the data and continuously learn from it to solve the problem. Instead of writing rules manually, we allow the system to discover patterns on its own. This technology powers systems today like fraud detection, recommendation engines, medical diagnosis tools, and even self-driving cars, if you've heard about Tesla. Yes, that is machine learning in a nutshell for you. For example, you would say, instead of programming, let's say, a system with rules to detect spam emails, you would say, let's give the system thousands of examples of maybe spam and non-spam emails, and it learns the patterns itself to differentiate the two. Machine learning today in the world comprises of three main types, but today we will talk about the two, that is supervised and unsupervised, leaving out the reinforcement. That what really makes the difference is usually how the system learns from data. For example, to begin with, supervised learning. Supervised learning deals with labeled data. It is basically like learning with a teacher. It requires a human level data set which provides the necessary supervision during training the algorithm or the machine learning algorithm. You will have input data. We have input data and correct answers, also called labels. The model learns the relationship between the inputs and the outputs. An example is email spam detection, maybe house prediction, house price prediction, credit scoring in finance. If you would give, I think, yeah, the basic example is like a student practicing past paper questions with against a marking guide, so that they will know if they have passed the question or not, to make sure or to evaluate if they have learned something. That is basically supervised learning for you. Yes, that is supervised learning. It also handles a continuous type of data. A continuous type of data, not discrete, but a continuous type of data. It deals with categorical data, data that is exclusive from each other. It can be numerical, but discrete and fixed in range. Yes, and then we come to unsupervised learning. Unsupervised machine learning, this deals with a data set with no labels, unlike supervised. It enables the algorithm to learn based on no supervision. That is to say, it is like teaching yourself without a tutor. The algorithm is given access to the data set without a target label, and all it has access to is what they call features, from which it will determine and pick patterns to define what the target label should be. It involves things like clustering, grouping together features that share the same characteristic. It involves things like anomaly detection, detecting an unusual occurrence of a data instance in the data set. An example, if you would say in the real world, is fraud detection. And maybe social network grouping, entertainment. For example, you would give an example like Netflix, that if they wanted to group a couple of users based on their preferences. Yes. We will go straight to the pipeline, machine learning pipeline. It's just a step-by-step process to build a machine learning system. Some of the major steps include, of course, getting data or collecting data, performing exploratory data analysis to discover patterns in the data. It will involve things like preparing the data, which is step number for the machine learning algorithm. It will involve things like, yes, removing duplicates, cleaning the data, and then you will go on to select the model you want to train and evaluate the success or accuracy level of the model against that data. And then the model will be presented after being trained and tested, and it will be deployed to make predictions on a new set of data. Yes. No. Future scaling, it is an essential step in preparing data before feeding it into the machine learning model, especially for algorithms that rely on distance calculations or optimization. It's important for algorithms like the k-nearing neighbors and SVM that rely on distance calculations. Yes. You can have normalized data, which is calculated using that formula, and standardized data. Below are some of the plots for non-normalized features and normalized features to see gradient descent with or without feature scaling. It's like converting all currencies into the same unit before comparing prices. Yes. What makes up a machine learning model? It is basically made up of three components. And the first one is the prediction model. You will have a cost function and the optimizer. The prediction model, of course, makes the predictions from the data fed to the algorithm. The cost function will measure how well the model predicts the training data. by comparing the predicted values with the actual target values. And the optimizer is in place to readjust the predicted value to get it as close as it can to the actual value. So it actually improves the model. It improves the model. Yes, there are two major types or categories of machine learning models, and one is the deterministic model. Yes, there are two major types, and one is the parametric model, where the structure is fixed, and the non-parametric model, where the data determines the structure. Of course, there is a deterministic model, one that deals with no randomness. It is suitable when the prediction error is negligible, and the probabilistic model that deals with randomness in the data. Probabilistic model types include regression models, correlation, and some other models. So when you go to regression modeling, it includes a few steps. And these steps include hypothesizing, deterministic components. You specify the probability distribution of a random error term, and you evaluate the fitted model. You use the model for prediction and estimation. It's like basically building a bridge. You design it, you test it, strengthen it, and then allow cars to pass over it. Yes, k-nearest neighbors, or you would say KNN. KNN predicts based on similarity. It looks at the closest k neighbors and makes a decision based on them. Just like the name sounds, k-nearest neighbors. Looks at the closest k neighbors. Step 1 is you calculate the distance between all training data and test point. Step 2 is you find the nearest k neighbors by sorting the pairwise distances. And in step 3, you classify the point based on a majority vote. An example is, let's say you are doing a medical diagnosis. If 8 out of maybe 10 similar patients had malaria, the new patient likely has malaria. It's like asking your closest friends for advice. Yes, we have the Manhattan versus the Euclidean distance. These are methods of measuring distance. Euclidean distance is it's basically a straight line distance, just like you can see in the graph or illustration there. From X to Y is a straight line. Manhattan distance is like moving along city blocks. It's basically like vectors, making vectors. Yes. And an analogy is Euclidean distance is basically a bird flying straight from point X to point Y. And Manhattan distance is basically like a car moving through streets to navigate its path to a certain destination. Yes, when we go to decision trees divide the input data recursively according to features. The data to arrive at a destination. They split data using a series of yes or no questions. Yes or no questions. An example is a bank loan approval system. It's like going through 20 questions to arrive to guess an object. It's a yes or no issue. Is it this or this? Yes or no? Is it a cat? Yes or no? Does it have ears? Yes or no? Something like that. Yes. And we'll go straight to the ID3 algorithm, which is the iterative dichotomizer 3. This algorithm is a method used to construct these decision trees from a given data set. It works in a way that you find the best feature, you find the best split for the best feature, you partition classes based on the previous two steps, 1 and 2. The stopping condition or criteria is that the recursion continues until one of the criteria is met. And then we have ensemble learning and random forest. Ensemble learning combines multiple models to achieve better accuracy and robustness than individual models. It mainly has two major techniques, which you would say are bagging and boosting. Bagging is basically creating multiple independent models using random subsets of data and aggregate results such as average for regression and majority vote for classification. Boosting, on the other hand, builds models sequentially, where each new model focuses on correcting the errors of the previous ones. On the other hand, if you go to random forests, it is basically an ensemble method based on bagging. That is why we stated two main techniques, because random forest is based on bagging and it builds multiple decision trees during training and combines the output for better accuracy and generalization. It's like, if you would say, asking multiple, if you are a medical worker, it's like asking for advice from multiple doctors before coming to a conclusion on a diagnosis. You go through very many separate routes and combine all to come up with one decision, hence giving you a better accuracy and generalization. Some of its key features include reduced overfitting. It reduces overfitting by averaging predictions. Each tree uses random subsets of features, improving diversity and generalization. It's effective for both classification and regression tasks. It has the following advantages. It has a high accuracy because of the multiple decision trees and robustness. It works well for both classification and regression tasks. It can handle nonlinear relationships very well. Some of its disadvantages or cons is that it can be computationally expensive with large datasets or the many trees that are being generated. Interpretability is lower compared to single decision trees. And then we have boosting and AdaBoost. Boosting is an ensemble technique where models are built sequentially, and each model tries to fix the mistakes of the one before it. It's basically like having software and upgrading it, getting new releases over and over. So AdaBoost, or you would call adaptive boosting, is one of the earliest and simplest types of boosting algorithms. It focuses on adjusting the weights of data points based on how difficult they are to predict. Key features of this AdaBoost are that it combines many weak models like small decision trees into one strong model. It's basically like averaging. Models that perform better are given more importance in the final prediction, and it works well for both classification and regression models. Then we go to support vector machines, or you would say SVM. This finds the optimal hyperplane or decision boundary to separate classes with the widest possible margin, or you would say maximum margin. An example would be text classification and handwriting recognition. There are a number of types of SVMs, and one of them is the linear SVM, which works best when data can be split with a straight line. The nonlinear uses the Keno trick to transform nonlinearly separable data into a higher dimensional space where a linear boundary can separate the classes. Yes, and when we talk about the Keno tricks, these are basically mathematical functions that map data to higher dimensional space, making it possible to classify nonlinear patterns. Common Kenos include the polynomial Keno, the GRBF, or the Gaussian radical basis function, the sigmoid Keno, and the causing similarity Keno. Some of the key features of the support vector machines include a hyperplane. This is a decision boundary, or what we called, yes, a linear boundary in the previous slide, separating the classes. They include a margin, and this is the distance between the hyperplane and the closest data points, e.g. hard and soft margins. They include support vectors, the data points closest to the hyperplane. Key hyperplane parameters in support vector machines are C. Yes, this can be viewed as a way of controlling overfitting. There's a gamma hyperparameter. This controls the distance of influence of a single training point. Low values of gamma indicate a large similarity radius, which reduces in more points being grouped. For high gamma values, the points need to be very close to each other to be considered in a group or class. This is basically like lifting data into a new space where separation becomes easy. And yes, data standardization. Data standardization is a pre-processing step where we transform data to transform the data to have a mean of 0 and a standard deviation of 1. Standard deviation of 1. This ensures that all features are on the same scale. What is the importance of data standardization? It ensures that all features are on the same scale, preventing larger values from dominating. It improves the performance of models relying on distance calculations such as the SVM, KNN, etc. And how do you do that? For each value of the feature x standardized is equal to x minus the mean of the feature divided by the standard deviation of that particular feature. You will have to note that we use standardization for algorithms that are sensitive to feature scaling, e.g. SVM. It is not required. Data standardization is not required for tree-based models, for example, random forests, or bagging, or boosting. Yes, and we have lastly, principal component analysis, or what you would call PCA in short. The goal of this is to reduce dimensionality of data while keeping information loss to a minimum. It assumes that the variables are linearly correlated. If the correlation is not linear, then PCA will not be efficient. So basically, its role is to reduce dimensionality while keeping important information. An example is image compression and face recognition. It's like summarizing, you would say, let's say a 200-page book into 20 pages without losing key points. It simplifies data while preserving meaning. Some of its applications include image compression, and you reduce storage by keeping the most informative parts of an image. Another one is exploratory data analysis, where you identify patterns in high-dimensional data sets. Another is noise filtering. You remove less significant variables, e.g. background noise, in signal processing. For example, what is applied in Zoom, where they have noise cancellation. And some of its benefits are dimensionality reduction. It simplifies datasets with many features. It eliminates redundancy because you remove correlated features. It speeds up models. You reduce computational cost for large datasets. And it also improves visualization. It projects high-dimensional data into 2D or 3D for easy understanding. Basically, in conclusion, machine learning enables computers to learn patterns from data and make intelligent, or you would say, informed decisions. From the likes of the k-nearest neighbors to SVM, from random forest to PCA, each algorithm solves problems in a unique way. And our basic understanding of these concepts equips us to build smarter systems and solve real-world challenges in various sectors today. Thank you so much for viewing.